Okay, so welcome everyone to the IARCS verification seminar. So today we are happy to welcome Nathanael Fijalkow from University of Bordeaux and the Allen Institute of Data Science in London. So he's well for his results in probabilistic automata. Look forward to results on neural guided program synthesis. Yeah. So off to you, Nath. Yeah.
Thanks a lot, Shri, and thanks everyone for coming. It's very nice to come to your verification seminar series. Yeah, so I'm going to talk about the recent work that's published in AAAI with a lot of different people, and one of them I just mentioned is an Indian student who came for an internship to us in Bordeaux, and that's kind of one of the outcome of this. All right, so I'll talk about neural guided program synthesis. And as Shri said, I'm doing probabilistic automata, so don't worry, they're hiding somewhere just behind the corner. Okay, so this is all in one slides, sort of what I believe in and what this work is about. On the one hand, we have machine learning that's known to be very efficient, but not as reliable as formal methods. And somehow the future is somewhere in between, right? The future is in trying to combine these two strengths, efficiency and reliability. And somehow there are two ways to look at this. Either you go from formal methods and you move to machine learning and you say, well, I'll use some formal tools to improve guarantees. Or you kind of go the other way around and you say, well, improve performance using machine learning of formal methods techniques. So this is, the kind of direction we're following here. I'll be telling you about a program synthesis where we have, a set of very nice formal methods, techniques, and then I'll kind of talk about how we can enhance them, improve them using machine learning, and how they kind of naturally combine, and what are the challenges of doing so. Of course, anytime, please ask questions. If anything is not clear, I'm happy to take any questions. All right, so the abstract promised something funny, that there's a surprising connection between airport screening, DNA sequencing, and program synthesis. So actually, this is kind of rewriting the history, because in the paper, the AAAI paper, we're not talking about any airport screening. But after it got published, we realized that one of the contributions actually existed for airport screening. And I find this story fascinating. So I will tell you the story, how it kind of existed from airport screening question, and then sort of translate it back and show that it's really exactly the same question in program synthesis. So now a quick disclaimer, the following example is real, as in it was published in a conference that seems to be a very applied conference where this kind of ideas were actually being used in airport screening, but it does not reflect in any way my own political views. So this is the problem. You have a population of individuals coming in and out, the airport. And potentially some of them are terrorists. And then the question is, you want to check, you want to scan people in order to know if they're terrorists, but you cannot afford to really scan everyone. So what you want to ensure is, I will scan kind of as little people, as few people as possible, in order to catch terrorists. And of course, said like this, there's not much you can do. But there's a kind of assumption, and this is where it gets a bit dodgy on the, let's say, political side, but let's not think about it for now. So this is just assume we have a prior. So over your population, there are different types of people. Here, for simplicity, I will just talk about men and women, but could be any other features you have on people. And think of this as some Bayesian information. You have some likelihood about people being terrorists. So, let's say men are 9 times more likely to be terrorists than women. Now that you know that information, how should you actually scan people? And that's exactly, that's the whole question. So let's, look at it a bit more formally. Formally, you have a distribution D over some population X. So X could be finite or could be infinite. And you have this distribution D, that's your prior. So this is kind of information you have that gives you some probability that if you pick someone, then this is a terrorist, right? And now given D as your prior, how should you scan people in order to, as quickly as possible, detect terrorists? So a bit more formally again, we want to look at sampling algorithms. So you will just take from your population one individual, check if it's a terrorist, scan through whatever gates, and then just put him back, and you will do this with replacement. So this is some kind of strong assumption. Why don't you do it without replacement? Meaning if you have taken someone, then you're not going to scan it again. But there are some good reasons actually on the program synthesis side why you don't want to do without replacement. So we'll look at sampling with replacement. And now the goal is to minimize the following quantity. This is the expectation of the number of scans you do before you catch a terrorist, right? And here I put expectation because there's, this prior is a probabilistic distribution. So this is an expectation over that probabilistic statement together with possibly the use of randomization in my algorithm. So find an algorithm minimizing the expectation of the number of scans you make of people before you catch a terrorist. And this quantity, we call that the loss, right? So now, I would say, long story short, this is maybe a bit quick, but the naive algorithm would simply say, well, I sample according to my prior distribution D. So if I believe that men are 9 times more likely than women to be terrorists, then I scan men 9 times more often. And it turns out you can do the calculation. It's not too hard to do this calculation by hand. It's actually suboptimal. The best sampling you should do is what we call the square root rule. You should sample individuals with the square root proportional to the square root of the probability. So I define this distribution that I called square root of D, and square root of D for some individual X is proportional to the square root of the X. So proportional means that you just divide by this normalizing factor. If it exists, I'll just skip over those details. And you can show that for the loss that I defined above, this actually is optimal in the sense that this is the best sampling with replacement strategy for catching terrorists. I think there's an issue. I know. Okay, fine. All right, so maybe let me give a very simple example of the square root sampling theorem to kind of convince you that there's something to it. So we're talking now about a very, very simple case where we have just a population of 2 individuals, so just head and tail, right? And the prior that's here is just telling you with priority P, head is the terrorist, and with priority 1 minus P, tail is a terrorist, right? Now you know this, you know P and 1 minus P, you don't know who's the terrorist, and you're supposed to sample heads or tail. So you're supposed to give a priority P prime to sampling head and priority 1 minus P prime to sampling tail in order to get as quickly as possible, understand as quickly as possible whether it's head or tail who's the terrorist. So if you do the calculation, there's something funny that happens, is that what you're actually trying to minimize is this formula here, because with priority P, this is head, and then it's going to take you 1 over P prime number of tries to find the right the right answer in that case. And then in the other case, it's 1 minus p and 1 minus p prime. And that gives you, when you try to minimize this as a function of p prime, then the optimal is this funny square root of p thing. So this is sort of the conclusion of that paper. There, it says if men are 9 times more likely to be terrorists than women, then they should be scanned 3 times more often. So square root of 9 times. All right. So that thing here is, I kind of summarized what this airport screening paper was about. And now I will kind of just translate all of this into program synthesis. Okay, so what is exactly the problem that we're looking at here? It's called inductive program synthesis. So first of all, I fix a domain-specific language. So we call that a DSL. This is just some sort of, you fix the programming language that you're working with, and this is parameterized. Your problem is parameterized by this. Now what you have as input is a few examples. Yeah, so I'm sorry, I think my video freezes regularly. It's frozen again. I can try to turn it off and on, but it usually doesn't work for too long. Now I think it's fine, right? Yeah. Okay, so sorry. So back on. So we have a few examples. So, let's say 2 inputs and their corresponding outputs. And you're trying to synthesize a function that satisfies this example. So let me give you an example here. Imagine you're manipulating programs that take as input a list of integers and output another list of integer. And what I'm telling you is, look, on this input here, I want to input 2, 4. And on this list here, I want to output this. So now you can look at it for a bit, and then you see, well, okay, so what's going on? It looks like this 4 and 2 appear here, but reversed. And then similarly, we have the 0, 6, and 8 that come here. So one possible solution is to say, well, first of all, I sort the list, right? And once the list is sorted, then I just remove all the elements that are odd. So I do a filter even, right? So that would be one solution program. But of course, since I have only 2 input outputs, then there can be many more programs. And the question here, at least the theoretical question, is really to find any program satisfying the examples. So it doesn't matter if there are possibly many solutions. Okay, and the whole approach that I'm interested in here is called the neural guided inductive synthesis, where the whole architecture is divided into 3 parts. So we have at the center, and this is kind of the most important, a symbolic search algorithm, right? So what I have here is a bit of a spoiler. I will talk in a second about program representation. So how do I represent my programs? But I can tell you already, I have some sort of grammar. This grammar represents all the programs that I can write. And searching here really means that I'm doing a symbolic search over the set of terms that I can generate in that grammar. Okay. Now, when I search, I can output some candidate programs, right? And if I do so, I feed that to the box on the right, which is the evaluation part, where I just check whether my program satisfies the specification, which in that case is just a bunch of examples. So I just check whether it satisfies these examples. And if it does or doesn't, then I get some feedback. If it does, then I have a solution, I output it, I'm happy. If it doesn't, then maybe I can, sort of get to know, was this an interesting candidate program, or so on and so forth. And now the kind of novelty, the important thing here is that the search is influenced, impacted by machine learning predictions that are happening here. So I'll talk more about where these predictions are coming from, but for now, the idea is that the predictions are ways of looking at your search procedure and prioritizing the search towards more interesting programs, right? So the predictions are not supposed to be telling you, this is the program. They're supposed to tell you, well, it looks like the program is in this direction or that direction. So this is really just sort of hunch on where to look. And this is prioritizing the search, but this is not removing part of the search tree. So now the first kind of practical instance realization of this neural guided program synthesis was by Deepcoder in 2017. And the key idea was that if you look at this example that we had before, you can look at these things here. And if you feed these two things to a neural network, then they will be able to find patterns, emerging patterns from this data. And from these patterns, they will be able to predict what kind of primitives are used in a candidate solution program, right? So you look at this and you say, well, I don't know what's the program. The neural network that will do the prediction doesn't know what the program is, but it says, well, looks like, all input are sorted. All output are sorted. And this is, some kind of intuition that probably there's a sort somewhere in the program. And then similarly, it sees that all the values that are in the output are already in the input, and they're all even. This again is some kind of suggestion that probably somewhere in the program there's a filter even primitive. So this is kind of the intuition of these machine learning predictions. They are supposed to look in the examples for patterns that reveal the use of some primitives used in a solution program. All right. So now I'm talking a bit about program representation to kind of ground this a bit more concretely. So what is a program in this case? As I said, we will fix some DSL. So DSL is a domain-specific language. That means that for any task you may have, you have to design this DSL. What does it mean to design a DSL? It's to give a list of primitives. So in my example above, I had programs manipulating list of integers. So typical primitives I could use would be sort, map, successor, and so on and so forth, right? So giving a DSL is giving this list of primitives, and it's very useful to strongly type these guys. So for instance, a sort is a primitive that takes a list of integers and outputs a list of integers, and so on and so forth. And you can see here, you have, potentially polymorphic types, and you can have complicated high-level primitives there, right? Now, once you've done that, once you have fixed your DSL, then you can do this compilation phase that turns this DSL into a grammar, a context-free grammar. This is some kind of very classical way of dealing with a programming language. Now you have finite description of all the programs you can write that are well typed by construction. So for instance, here, if I'm saying, I want a program that outputs a list of integer, then I can just write a sort, and then I just need to produce another program outputting a list of integer, and so on. So this is some kind of syntactic rewriting of the DSL that I had here. And this is a representation of all the programs I can write. Now CFG kind of generates a set of terms, and those terms are the programs I can write. Okay, good. Now, where are the predictions? For predictions, we'll be moving from context-free grammars to probabilistic context-free grammars. Right? So this is a toy CFG, which has two primitives f and g, and two constants a and b. So for instance, in that concrete CFG, I can do two programs. So this term here is one program I can generate with this CFG, and this one here is another one. Okay. Now, this is a non-deterministic process. So this is a way of generating all terms. Now I will make it, instead of non-deterministic, I will make it probabilistic. So how does that work? Well, I will simply add probabilities to all the possible derivations I'm making. So if I'm in the non-terminal S, I can generate either F, SS, or GT. And for each of them, I will just give some probability. And the idea is that for every line, this should sum up to 1. This is with priority of 4th, I generate F, and with priority 3/4, I generate G. And now that means that this process becomes a stochastic process. So in effect, a PCFG induces a distribution over trees or terms, however you want to call this. I think the best name in that context would be programs, right? Okay. So now we can talk a bit more about what the predictions are doing. So prediction, I have this prediction model here. So typically we'll use a neural network, but there are also other possible choices. Now this prediction model will take as input examples. So you take, in my example before, I take these two input outputs lists. I encode them and feed them to my neural network, this prediction model. And what is outputs are probabilistic weights that I can feed to the context-free grammar to make it probabilistic. Right, so let's exemplify this here. If to my prediction model, I feed these two lists, these two pairs of input outputs, then this will give me values, this will give me probabilities for every, for instance, for every pair of primitives that one follows another. So for instance, if I feed this, then I hope that my prediction model will tell me, well, there's a high probability that after a filter, you use a sort. And on the other hand, there's no probability that after reversing the list, you use a sort. Right? So the prediction model will give me for any pair of primitives or any tuple of primitives, what's the likelihood of them appearing in my solution program. Okay.
Nathanael, can I ask a question?
Sure, please go ahead. Of course.
If you have a neural network here for the prediction, what are the outputs?
So the output here will be, so more concretely, you'll have to fix, so it's going to be R to the D, where D is the number of derivations in the CFG you started with, right? So the CFG, that's the compilation of your DSL. And for each of these derivations, you want to have a probability. So this will be a logit. For each derivation, you'll get logits that tell you how likely it is to use that derivation in a solution program.
And
so it's going to give you a vector.
Kind of a bounded depth.
Yes, that's going to be bounded depth because this CFG here is fixed, right? You fix that up front. You say, I fix my programming language, and okay, this is one task of integer manipulating lists. So I fix that, and then the CFG will be fixed, so it's a bounded size vector.
Thanks.
Yeah, thanks for the question. So in effect, what this prediction model does is it gives you a probability, a conditional probability. It looks at the examples. You feed the prediction model with the examples, and then it outputs a distribution, a prior distribution over programs, right? So it's telling you for every program how likely it is that this is a solution program for the examples it was fed. Okay. And now that means that once you fed your prediction model with the examples, you have a prior distribution over programs.
So can I ask a question here?
Sure, of course. Please go ahead.
Yeah. So do you assume that the prediction model is already available, or is this prediction model constructed in some way?
Very good question. So no, I mean, we'll construct it as a pre-processing phase. We'll have to construct it, and that's actually a very difficult task. And this is a very widely open question, how to do this as efficiently as possible, because well, to be honest, the state of the art of prediction models is not very accurate. So you will not get very, very good predictions on your programs. What you will get is something like, better than random, better than uniform predictions. But as I'll show you a bit later in some diagrams, this actually makes a huge difference. So even if you get just a bit of an edge of where to look for, where is the right program, then actually that will help quite a lot. So now going back to your question, do we assume it exists? No, we have to build it. And that asks a lot of questions. For instance, where do you find your data for training it? And of course, what kind of architecture, how do you train that? So I will not talk about this too much here, but this is a very, very interesting and I would say widely not so understood question.
Okay, thanks.
Yeah, thank you. Okay, so now we are sort of back to a situation which looks very similar to this airport screen, right? We have a set of programs, which you can think of as the population, and we have a prior distribution on it. So we have some prior that for every program, it tells us what's the likelihood of this being a solution. But now we have to perform the search, right? So we have to decide which programs to check against our specification and in which order. So this is the main question that we were looking at in this paper, how to deploy the prediction model. So this is a purely algorithmic question. Now assume that I have a prediction model. And in that case, as I said, the prediction models gives me a PCFG, so a probabilistic context free grammar. And now that I have my probabilistic context free grammar, how do I, what algorithm do I use to enumerate my programs, to choose which programs to output as candidate programs? So to show you that this is not an easy question, let's take a very simple example. Imagine that your set of programs is just all natural numbers except for 0, right? And now the probability that the natural number you're looking for is n is 1/2 to the n, right? So the most likely program is a half, is n equals 1 with a probability half, but every natural number is possible. And now obviously, the most natural thing you could do if you're just looking for the program is just enumerate them in order 1, 2, 3, 4, because 1 is the most likely, then 2 is the second most likely, and so on and so forth. And if you do the math, then the probability, the number of programs you will enumerate before you find the right one is this infinite sum of n divided by 2 to the n. So this is 2. So an expectation, it will take you just 2 tries to find the right program if your prior is D. So this is for enumeration. Now, another strategy would be a sampling strategy with replacement. So you just sample a program. So you sample a natural number, let's say using distribution D, and you keep going until you find the one you are looking for. And now you do the math, and now this has infinite expectation. So it's going to take you essentially forever on expectation to find the right program. Now, third, you can use the square root rule, and instead of sampling with D, you sample with square root of D. So that means that you sample n with probability that's proportional to 1/square to square root of 2 to the n, and so this square root plus 1 is just a normalizing factor. Right? And now you do the math, it turns out that the expectation is 5. So that means, and this is, I think, a very surprising fact, that there is a sampling algorithm, so a very simple algorithm, that will find the right number in about 5 tries. And that is not an enumeration algorithm. And somehow, it's only 3 times worse. And this, I would say, is one of the key takeaway message of this work, is that, well, enumeration is a natural approach for program synthesis, but actually sampling can be very efficient and can be very attractive because it's extremely simple to implement and to parallelize. All right. So, like I was saying, there are kind of 2 approaches to the deployment question. Either you sample programs with some distribution based on the prior, and we've already established that the best distribution you should use is the square root of your prior, or you do an enumeration approach where you try to enumerate programs kind of deterministically, finding in a good order in order to, as quickly as possible, find your solution program or a solution program. All right, so now I'm coming to the actual technical contributions to the paper, but I will not go into any details of those. Those are actually sort of, work on grammars. So this is the technical contributions are algorithms for grammars. The first one is a construction of an algorithm that we call heap search. So this is a deterministic enumeration algorithm that takes a PCFG and will output all the programs in decreasing order of likelihood. So the first program output will be the most likely program generated by the PCFG, then the second one, the third one, and so on and so forth. And the kind of interest in this heap search is that this is a very efficient kind of implementation of this enumeration strategy that goes from most likely to least likely, that you can prove is optimal in the sense that it minimizes the loss that I defined originally. So it will find on expectation the solution program as quickly as possible. And we'll do this sort of very efficiently thanks to some good data structure that kind of combines heaps for every non-terminal and shares information across them. Now, the second thing is a pre-processing phase. This is how can you, in this setting with grammars, with PCFGs, how can you efficiently divide your search across parallel architectures? So imagine that now you have 12 CPUs. Can you actually do your search independently in each of them? So we have a procedure that takes a PCFG and partitions the PCFG into 12 or K PCFGs in such a way that those derivations are done in a fair way. So you will have disjoint sets of programs that together form the original distribution and that you can spread across your different CPUs. And now the third thing is what I sort of already discussed at length. This is if you want to do sampling as opposed to enumeration, then the best is to do a square root sampling. And so the discussion here is how to implement it in the specific case of PCFGs. And you can show that actually you can realize your square root rule using a second PCFG that can be efficiently computed. Therefore, you have a very cheap and easy sampling solution, which is to sample from a second PCFG. So if you're interested in kind of the details, the gory details of grammars and how they work and how you do enumeration, then I'm very happy to discuss that later. But unfortunately today I don't want to go into this.
So just a quick clarification question there.
Yeah.
So the loss in the first one, the minimizing the loss. So I mean, I'm just trying to understand whether that loss is based on whether the loss function is kind of based on the efficiency, or is it really based on the prediction model, or
Very good question. And let me go back to the definition of the loss to highlight exactly that. Okay, so now you know, we're talking about terrorists, but obviously I can rephrase that. So number of attempts, meaning number of programs we check before finding a solution, right? So this, what you're trying to do is minimize this. This is the number of programs you will try before you find a solution program. So this is not talking about time computation. It doesn't talk about time. It doesn't tell you, you know, how long it takes to generate all of those programs. It only counts how many programs you tried. It doesn't talk about the space. It really is a measure of how many attempts you will make. And the idea, the intuition why you're interested in counting the number of programs is here. When you look at this pipeline here, sorry for the moving, searching that's here is actually a small part of your time. Most of the time will be spent on evaluation here. So this is why you want to spend, you know, you want to sort of find the programs that are the most likely, the most interesting ones. So your candidate program should be as good as possible in order to do as little evaluation as possible. And that's the reason why in this loss function, you're really only counting the number of programs you do. This will be the number of calls to your evaluation oracle. But now I will kind of back this intuition with some experiments to show you what's going on actually.
Okay, yeah, got it. Thanks.
Thank you. All right, so in that diagram, in that, yeah, I'm showing you a comparison of different search algorithms. So all of them existed except for heap search. That's our new algorithm, and this square root sampling, that's our new thing, although it existed in our report screen, right? So the other ones are sort of state-of-the-art algorithms in that setting. So what we do is we have 138 tasks, and for each of them, we get a set of examples. We run the prediction model, we get predictions, and now we're asking each of the algorithm to find a solution program. And then we compare as a function of time, how many tasks are completed, and we have a timeout at about 5 minutes, right? So for each task. So, okay, so what exists? A star is a good benchmark here because this is an enumeration algorithm that will do essentially the same as heap search in so heap search and A star do a very similar thing in the sense that they will enumerate the exact same programs in the exact same order. So they will give them to you in decreasing order of likelihood from the most likely to the least likely until the solution program is found or until timeout. And so you may be wondering, why is heap search so much better than A star? And the reason is that heap search uses a advanced data structure that actually strongly depends on the PCFG and strongly makes use of this recursive nature of the PCFG, whereas the A star is some sort of generic approach to how to do this decreasing likelihood of programs. Now, it's interesting to compare heap search to the threshold algorithms. Threshold algorithm is a very natural sort of incremental DFS algorithm. And it actually works very well. This is what's used in most of the Cygus solvers that use enumeration. The reason why heap search is a bit better is actually not so obvious. So let me get to here. Like I was saying, the first point is that A star and heap search do exactly the same thing. And the only reason why heap search is better is because it's faster. So it has better data structure. Now, the comparison between heap search and threshold search is completely different because they do completely different orders. So threshold search will be able to output much more programs. So in the same time, in the same time budget, you will be able to have 10 times more programs for threshold as compared to heap search. However, those 10 times more programs will be much less likely to be solutions. So in other words, the predictions that are given to you are sort of not taken into account so much by threshold search. Whereas heap search follows them as closely as possible by giving to you the programs in decreasing order of probability. So now what this shows here is that it sort of pays off to actually follow your predictions closely, because then you quickly find a solution program instead of trying a lot of programs and feeding them all to your evaluation, which is the most costly part of the program synthesis question. Okay. So here's a quick summary. We have a set of sort of generic tools for performing symbolic search on grammars. And the idea, the kind of game changer is that on top of all these formal methods approaches to doing symbolic search over grammars, now we can nicely combine them with these machine learning predictions that really boost sort of performances while keeping the symbolic search correctness and properties intact. So you can check out our tool that was done for this AAA paper. And the goal of DeepSynth was really to have a very generic way of doing this, so that you can really input any sort of DSL and immediately plug in prediction models. So in answering an earlier question, in DeepSynth, we have different methods that can be used to sort of off-the-shelf give you prediction models. Now, of course, in any concrete DSL, if you come up with better prediction models, then that will boost performances by quite a lot. So this is sort of where we stand today, and that's very exciting perspective, because now we can apply this sort of set of tools or think about other fields, other kind of symbolic search questions as in this context. So for instance, I mean, things that we're looking at the moment is how to do reinforcement learning using program synthesis. Similar question for reactive synthesis and specification mining transactions, or for that matter, any symbolic search question. How can we use machine learning predictions to boost the search? And are those generic tools that we develop for program synthesis useful in all those fields? All right, so that's all I wanted to say. Thank you very much for all the questions, and I'm happy to take some more questions.
Thanks a lot, Nathanael, for the excellent talk. So now we are open to more questions.
Nathaniel, I have a question.
Sure.
I wanted to understand this neural prediction part a little better. So we have multiple IO pairs, right? We are starting with that. So I guess so the input and output that is fed is in each row is essentially fed here, and then you are getting the probabilities for the derivations on the right hand side. So for the next row, I also get a set of probabilities, right? So how do we kind of or a set of inputs output pairs, how do you actually choose the overall? How do I add it?
Yeah. So actually, you do it the other way around. So if I the way you do this is your prediction model actually is divided into 3 parts. There's an encoder that will encode each of this pair input output. And then you will embed them, embed them all together, which actually means that you stack all the input output pairs together. So once you've encoded this, you will actually stack these guys together, and now you have sort of one vector, and this is what you feed to really the core prediction model. So you don't do predictions sort of independently for each input output. You do a sort of batch prediction or stacked prediction for all the input outputs you have.
So does that mean that the input side a finite number of inputs?
Yes, 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 it does. Yes. So
maybe some kind of transformer kind of thing you could use.
Yeah, it's not clear. It's not clear in which situation you will have a lot of input outputs. You know, so in typical examples that people take in this programming by example or inductive program synthesis question, they would say you have 1, 2, or 3, or maybe at most 5 input outputs. So it's yeah.
Okay.
But I don't know. I mean, if you have an example, a situation where you have more, then that's a good question how you deal with that. I don't know.
No, I don't have any example straight away, but I just wondering. Thanks.
Yeah, thank you. Sorry, my video froze. So yeah, I'm here. But
So Nathaniel, Deepak here.
yeah.
So how does this compare with these? I mean, this pros and stuff, right? The synthesis tools, the programming by example.
Yes.
Tools, which probably don't use probabilities.
Yes, exactly. So pros is very similar in the sense that it does all of this. So pros is all of that, right? It has a search engine that essentially goes through terms in a grammar, and then it has this evaluation box that typically will give you some good feedback on whether a program is a solution. And typically you will get, for instance, additional input outputs, right? If you have a CIGAR approach, then when a program is not satisfying your specification, then you will get an additional input output that witnesses that, and then you kind of iterate over the search. So PROS is sort of comparable in the sense that it solves the same question and approaches it in the same way. The kind of difference here is the use of these predictions.
So, I mean, in your comparison, did this do better than PROS on?
Yes, but it's a bit hard to compare exactly because if you want to compare, so I'm going here, if you want to compare, then you have to have equal situation. And that comes back to the question we had earlier, where is your prediction model coming from? So if the prediction model is typically trained on data, and if I assume that I have very good data, so if I have already, if I take, for instance, my 138 tasks, and I take half of them for training and the other half for testing, then I will do amazingly well. And then I will, indeed, those kind of techniques will beat existing purely formal methods tool. But this is a bit cheating because in reality, you don't have such a good training set.
Right.
So now what you can do is you can say that you will train your data, you will train on synthetic data. So you don't assume that you can use your testing set for training the prediction model, and then life becomes harder because the predictions are a bit worse, and so the comparison is a bit unfair in that situation. So I think you get sort of similar performances overall, but of course you have to pay this pre-processing time that doesn't exist in purely in prose, for instance, because you need to train your prediction models.
Right. Okay.
Hi, this is Ravindra. I have a question.
Sure.
So
please go ahead.
generally, program synthesis is used for with a small set of input-output examples, right? But your prediction model requires, if at all I need to build a prediction model, it requires a large set of data. So that is defeating the purpose of the synthesis approach, isn't it?
Yeah, so I think yes, in the sense that in many, so the prediction model will not be trained on, at runtime on your data. The prediction model will be trained beforehand on other data. And indeed, as you said, it asks the question where this data is coming from. And the answer we have today is essentially the best, the most realistic is to do synthetic data. So you just look at your context-free grammar, you try to generate programs that make sense, and this is what you use for training the prediction model, and this is what's going to guide your search. And this is already quite good. This is not as good as if you had a very good actual human-made training data, but this is already something. Now to the question whether that can be applied in synthesis world, in some papers, they actually show that in order to train these prediction models, you can simply, for instance, just take all of GitHub. That will give you, a lot of Python code, and this properly translated and cleaned, that's going to give you a big training data that you can then use for your prediction models.
And a related question. So, if typically when we write program synthesis, we will have our DSL, obviously tailored for a specific domain. So building large data, obviously the programs may not exist in that particular DSL. So then, creating synthetic data also is a non-trivial task, isn't it?
Absolutely, yeah, it's absolutely a non-trivial task. But I think it's not creating a problem. It's maybe showing that some problem already exists, which is that in a program synthesis question, designing the DSL may actually be the hardest part of the whole pipeline, right?
Right.
And the thing is that in that case, you pay for it already at the moment where you decide to train a prediction model. But in practice, you would pay for it later, because if your DSL is not expressive enough, or if it's, for instance, not succinct enough, or if it's not good for your task, then your your program synthesis will fail. So yeah, so I think it's highlighting an issue that already exists, that constructing a DSL is a very hard task.
So in your experiment, what kind of tasks? What is the DSL used? Is it a standard programming language or a subset of a standard programming language? or is it a...
No. Well, it's a standard benchmark in that area in the sense that, so this particular one that I'm showing here, this was list, like integer list manipulating program. So essentially this sort and so on. And this is some sort of classical benchmark. Now there are others. So the other classical one is the flash fill, that is text manipulation. So you have strings and you just try to edit those strings. There are actually quite a bunch of very diverse DSLs that you can play with. And I would say results are more or less consistent over these DSLs. So that's some kind of good indication that, you know, things are happening sort of, it's really a set of generic tools. It's not so much tailored to the concrete DSL. But what you raised is an interesting question. Do you actually have programming languages that really look like, is it just a part of Python? And I think the answer is no, and it should not be, because Python is a very general programming language.
Right.
And it's going to be very hard to do program synthesis in Python, you know, unless you have the power of OpenAI. But the fact that design very specific, domain-specific language is key to make this approach, this prediction approach successful. But I think more generally, program synthesis can be successful only on very concrete and very well-tailored DSLs.
Right. Okay. Thanks.
Thank you.
Yeah. Hi. This is Mansi here. So I have two questions. The first question is how would you ensure that when you create synthetic data, how do you ensure that you're covering the whole program space? How would you sample from your CFG such that you do that? That is the first question. And the second one is, if your programs are recursive in nature, how will you get probabilities over the production rules in CFG?
Very good questions. Very good questions and very hard questions. So, okay. So first question, how do you have a set of programs that sort of cover nicely the set of programming language you can do, the set of programs you can do? Well, I don't know. The thing that I can do is rather the opposite. So when I build my training set, what I ensure is, for instance, that any two programs are semantically different. And this is very important to do this on your training set, because if you give to your prediction model two programs that do the same thing, then the prediction model will be very confused. So in that situation, should I go left or should I go right? And you're sort of telling the prediction model, well, actually both left and right are correct. And that is very confusing for a learning algorithm. So I don't know how to have this coverability property that you're mentioning, that you really have kind of any possible programs or semantics that you can have in your programming language. What we can ensure is rather sort of properties of independence in your training set. But indeed, this is a very difficult question. So we had a paper a few years ago, 2-3 years ago, on data generation, specifically on that data generation question. And we suggested some use of SMT solvers in order to check a sort of coverability of the set of programs. But I would say that that was really just a first step in that direction, and this is pretty much an open question. Now, the second question about recursive programs. Or do you want to reply to that?
No, that's fine. Yeah, I mean, I'll take a look at that paper maybe.
Yeah, thanks. So about recursive programs, that's another very hard question. So yeah, so I don't know how to do this in full generality. The programs that we have here, typically in the DSLs and you know, in all the existing DSLs, text manipulating or integer manipulations, they are basically bounded recursions. And that's enough essentially because you have just a small set of examples, and you never need very large recursion. So you can essentially unravel your program, and then when you look for the program, you will look for it in a recursive form. So that's that. But this is unclear how to do fully recursive programs and how to use to do the search for recursive programs. I don't know how to do that.
Okay. Yeah.
Yes.
Thanks.
Thanks. Diganta had a question on the chat. When we say that the output probabilities give a distribution on derivations, are we assigning a probability on each substitution of the grammar, or the probability is more granular than that? So that's a very good question. They can be, so I can do this. Maybe I can use some picture that already exists. Yeah, so imagine what I can do is actually saying I can assign probabilities to each node, right? This would be exactly doing a PCFG, but you can actually be a bit even more granular than that. You can do what we call diagram things. So you can say, I want to know the probability that I have F and F just after that. And similarly, I want to know the probability that I have G and then F, that I have F and then G after that on the right position. And somehow you can do this for any kind of depth you want. So you can really talk about the probability of generating a subtree or generating any kind of pattern you want. And that can be very useful because in many programs, you actually have strong dependency between the primitives you use, right? So, yeah, I mean, I don't have a good example on the top of my head, but you observe that in many programming languages, some primitive is often followed by another one, in which case you want your prediction model to be able to couple these two predictions. So indeed, you can have a stronger granularity in your predictions, and that can help a lot. Yeah, thanks for the question.
This is Ravindra. I have one more question. You said you have some intelligent data structure or nice data structure that give you a lot of boost of the your heap search over the other one. What is the data structure and what are the kind of characteristics that makes this very intelligent?
So here's okay. So here's an idea. Imagine that you have your PCFG. So you have your grammar. You have S, T, R, P. Those are non-terminals of your grammar, right? And so that means that when you can generate programs from S, actually, a program from S will contain programs from T, from R, and so on and so forth. Now, the kind of key idea that's here is a very classical one in grammar manipulations, is that instead of storing from S all possible programs that you have enumerated so far, because that's essentially what you need in order to enumerate a new program, then you will spread this. So you will say, I have one heap. So I have heap S that stores information about all the programs I already generated from S. But this does not contain all of the programs. It actually contains a list of pointers to various heaps below. Right? So we'll have one heap for each non-terminal. And those heaps are sort of connected in the sense that every heap contains information about, this is the set of programs that I have generated, but I don't store the whole program. I store only what I need to store here, plus pointers to other heaps below. And so the sort of, the algorithmic challenge here is to construct this heap, keeping as little information as possible in order to be able to solve the following question. If now I give you a set of programs that I have already generated, so which are stored in these heaps, can you generate the most likely program that has not been generated yet? And somehow what we show is that you can do this by calling only log of t number of heaps, where t is the number, the number of programs you've already generated. So you get sort of a delay of log of t. If you want to generate the tth program in your list, the tth most likely program, then it's going to take you a complexity, time complexity that's proportional to log of t. I don't know if that was not a bit too high level. Yeah.
Okay, I understood somewhat, but probably I didn't get the paper.
Yeah, so thanks. That's kind of the main part.
Is
of
it something
I'm
related to version space algebra like structure,
yes.
or these E-graphs? The recently came E-graphs, right?
The dream coders E-graphs, yes. I think in some sense it is, although E-graphs are talking about lambda calculus and sort of relate to the beta reduction. These heaps are very specific to the context-free grammar, to grammars. So I think it's not exactly, I mean, it doesn't technically relate, but there was some, the idea kind of also flew from that direction.
Okay.
And actually there's an author in common from both papers.
Right.
Yeah. So thanks, Nathanael. I think we had a good talk and an interesting round of discussions. So maybe one last question. Diganta has a question on the chat.
Very good question, Diganta. And actually, shamefully, the answer is no. So at the moment, when the program is wrong, so this is a Boolean answer. Yes, it's correct. We stop everything, we output the program, and we're good. If the program is not correct, then at the moment, DeepSyn just tells you, okay, well, wrong shot, just try again. I'm very interested at the moment in the question, what do you do? Can you actually get any sort of influence on the search from a program that doesn't meet the specification, but meets it halfway or something, which is not well defined in general. So, maybe if you have 5 examples and you satisfy 2 of them, then that program is not complete rubbish, right? You should use some of it. At the moment, I don't have a good answer to that. There's a NeurIPS question, a NeurIPS paper recently that addresses that, but it's not a very general technique for all of, independent of the DSL. So yeah, that's an interesting question. I don't know much about it at the moment.
Okay, great. I think we are running out of time. Yes, so thanks a lot, Nathanael, once again. Yeah, so let's.
Thanks everyone, and thank you, Shri, for the invitation.
Yes. So thanks everyone for joining the seminar. So see you next month.
Thank you.